All right, so first we have Professor Linic from the University of Michigan. So take it away.
Great. Thank you, John. Thank you, Hong. And thank you for inviting me. So what I'm going to talk about today is basically just some collaborative work that I've been doing with Brian on kind of shedding light on chemabsorption using machine learning. And really the motivation here is really to ask a question, can we use this tool to kind of reproduce what we already know about chemabsorption? And can we design workflows that can get us to these answers? And then towards the end, I'm going to have one slide just talking a little bit about just large argument models to mine for catalysis literature. So this is going to be a very short kind of 4-story discussion. First, I'm going to talk basically same thing that Brian did yesterday very briefly, remind you of the use of this interpretable machine learning to identify structure-function relations, and particularly relating composition of metal alloys to chemabsorption. Then I'm going to shift gears a little bit, talk about unsupervised machine learning workflows to identify electronic and geometric descriptors of chemabsorption, kind of seeing if we can reproduce the D-band model of chemabsorption. I'm going to have one slide on machine learning for accelerated discovery, where we used some Bayesian optimization to identify stable materials for electrochemical water oxidation reaction. And then I'm going to finish by very recent work that I'm doing with one of my students, which started last year, on kind of exploring LLMs for text mining of catalysis literature. So this first question, I think Brian kind of outlined this yesterday, is we were asking a question, how does the absorption energy of an adsorbate on a catalytic site change as we change the local environment of this site? And if you're doing this kind of using a pen and paper, the way physicists would do is you would say, well, I'm going to relate geometric structure to electronic structure, and I'm going to see how this electronic structure changes as a function of geometry, as a function of changes in these active sites. And I'm going to see how this electronic structure then changes adsorption energy. And then I would hope to establish certain correlation between electronic structure, adsorption energy, and electronic structure and geometric structure, and kind of derive these relationships. And this is really how most of these chemabsorption models have been derived previously. What we wanted to do in this work is really try to go directly from geometric structure to performance, from geometric structure to absorption energy. And Brian kind of discussed this yesterday, and we use this interpretable machine learning using these IGAM models. And the idea here is really to fit your energy, absorption energy of various adsorbates using this kind of function, where you have a linear combination basically of functions that are function of only one input variable. So in this particular example, we had the 9 input variables, and these are tabulated values of various properties of certain elements in periodic tables. So we input tabulated values of, for example, strain, electronegativity, for example, of the metal that's directly binded to the adsorbate and the neighboring ligand element, and then also size and extent of the d, s, and p orbitals, how far these orbitals spread in space, and also number of s, d, and p orbitals. And using this IGAM model, we can basically identify which of these variables are the most impactful in describing the chemabsorption process. And it's kind of summarized here. And what you see here is that really you can capture chemabsorption by focusing on essentially 3 variables. One is the change in the strain. The other one is the extent of the d orbital. So, for example, how far this ligand d orbital extends in space, and this has to do with width of d band. So it's kind of what you would expect if you kind of think about the d band model of chemabsorption. And another one is change in the number of ligand d electrons, the number of d electrons of the ligand atom. And Brian kind of explained this very nicely yesterday. More recently, we kind of try to expand on this work and try to now include electronic structure and kind of take a path that a human would take. Let's kind of start with the geometric structure, calculate electronic structure, expand this electronic structure in terms of principal component using principal component analysis, and then ask a question how these principal components can relate or explain the performance in terms of adsorption energy, and how they can explain geometric structure, and then ask a question, can we relate the two by using these principal components? So here is now the adsorption energy now as a function of the principal components of the electronic density of states of the surface sites onto which we are binding an adsorbate in this particular case. So as you see, the adsorption energy can be captured very nicely by using 2 principal components. We can capture a large fraction of the adsorption energy, And as you can see, as the absorption energy kind of becomes more exothermic for many adsorbates, this first principal components increases in value. And also the second principal component, increases, leads to weaker chemisorption. So now we ask a question, how do these principal components, which I said before, capture the adsorption energies quite nicely, relate to electronic structure? And what we see here is that actually this first principal component is very closely correlated to the center of the D band. And second principal component also has some correlation with the center of the D band. The first principal component, furthermore, is correlated with the width of the D band. So based on this analysis, if you didn't know anything about D band model of chemisorption, you would basically conclude that center of the D band is very important when you want to capture the chemisorption threads across different elements or different alloys in the periodic table. You would also conclude that the center of the D band is actually correlated to the width of D band. The narrower D band in general is going to lead to the higher center of the D band for a given number of D electrons present in the system. Furthermore, we also can kind of extend this to the geometric structure and ask a question, how do these principal components respond to the changes in the element or metal that's directly bonded to the adsorbate? And basically what you conclude is by doing an analysis that increasing the number of D electrons in this element that's directly bonded to the adsorbate leads to lower second principal component and weaker chemisorption. And then you can also conclude that for a fixed number of D electrons, decreasing atomic size leads to higher first principal component and stronger chemisorption. And this is actually very consistent with the D band model of chemisorption. If you move in periodic table to the right and up, you're going to have a stronger chemisorption, and this is actually what's telling you that. You can also see how this ligand atom impacts chemisorption. So what we found based on the analysis of these principal components is that increasing the number of D electrons leads to higher first principal component, stronger chemisorption. Meaning if you have a ligand atom and you're moving in the periodic table from D5, D6, D7, D8, D9, you're going to have a higher first principal component and stronger chemisorption of the atom that's binded to that ligand atom. And then for a fixed number of D electrons, increasing atomic size leads to higher first principal component, stronger chemisorption. So if you move down a column of a periodic table, let's say from copper to silver to gold, you're going to have increased atomic size, which leads to higher first principal component and stronger chemisorption of the elements that ligand atom is connected to. The third story is basically using active learning to try to identify some stable iridium alloys for OER. So this is the workflow that we used here, again, in collaboration with Brian. And the idea here is to start with a very small number of density functional theory calculation, use Gaussian process regression, and basically employ this workflow with Bayesian optimization to limit the number of density functional theory calculation that you need to do to identify stable iridium alloys for this reaction. And the reason why you want to have iridium alloys for this reaction is you really want to have materials that can perform this reaction with high chemical activity and at the same time employ less iridium than electrocatalysts that are employing purely iridium. So based on these studies, we identified a few materials that are stable and active for this process. These are multi-metallic oxides that contain iridium, and the ones that we focused on in studying in this molybdenum iridium alloy. So this is molybdenum iridium mixed oxide, and we actually tested this in ORR and does perform a little bit better compared to pure monometallic iridium oxide, and performs better from a perspective of stability. Basically, it leaches into solution with slower rates, which we predicted based on these simulations of formation energies. And also it performs better in terms of having a lower over potential for this particular reaction. So I'm going to finish today with just very recent work where I've worked on one of my PhD students on this, and he just started last year. And basically the idea here is, can we use already published material, data that's already published, or papers that are already published, and text mine through this data to get certain ideas about identifying some catalysts for specific reactions. And I can tell you that this is not simple. I mean, we encountered a bunch of problems that we didn't think would be there. So for example, really there's no uniform methods to retrieve articles to contact the publishing agencies and get the articles. Also, there's no uniform format in the form of that you're getting these articles. Some of them are HTML, some of them are plain text. You really want plain text. And also, from a legal perspective, there's really no uniform policy depending what publisher you're dealing with and depending what agreement your university signed, that can limit you in what you can share and you cannot share with the community and what you can publish and not publish. So I think these are things that can be addressed relatively easily, but it will take some action on the part of some stakeholders to kind of address these issues. Furthermore, you have to accomplish a number of objectives to make this useful, and we are kind of working on all of these things that I've outlined here, and I'm not going to go in detail because I don't have that much time to discuss this further. So here I'm going to stop and hopefully we can move on.
All right.